Part 2, Confidence Intervals. I'm Dennis Davis. In Video 1 on the sampling distribution, we considered a population and described the characteristics of a sample drawn from it. In Video 2 and 3, we're going to go backwards. We'll examine the characteristics of a sample and make inferences about the populations from which that sample could have reasonably been drawn. This is where inferential statistics, or statistical inference, gets its name. To infer something means to draw a conclusion based on observed evidence and prior knowledge. For example, if you see smoke, you may infer there's a fire. The smoke is the observed evidence, and knowing that fire makes smoke is your prior knowledge. In inferential statistics, the sample is the observed evidence, and knowing something about probability and statistics in general, and the sampling distribution in particular, is our prior knowledge. We'll make inferences about the population based on a sample and our knowledge. There are two types of inferences. This video covers confidence intervals. The next video will cover hypothesis testing. The topics in this video are point estimates and interval estimates, confidence levels and alpha levels, confidence intervals and confidence statements, margin of error, critical value, standard error, sigma known and unknown and t-distributions, and confidence intervals for proportions. Outline on the left, vocabulary words in yellow. We're almost ready to create a confidence interval. One more thought experiment, and then we'll put the pieces together. Suppose we have a golfer who's so good that if we gave him a target on a driving range, he can hit the ball within 5.28 yards of the target 80% of the time. So if he hits shot after shot, we can expect that 80% will land within 5.28 yards and 20% won't, no matter where the target is. Now, suppose we don't know where the target was, but we know the golfer hit one shot that landed here. Where do you think the target was? Was it over here? Over here? Maybe, but probably not. The golfer has a high likelihood of landing closer to the target. In fact, our prior knowledge tells us that there's an 80% chance that the golf ball is within 5.28 yards of the target. Suppose the golfer's shot landed at 124.73 yards. If we had to guess where the target was, this would be our single best guess. This is called a point estimate. A point estimate is a single value used to estimate a target, usually a population parameter. Due to natural random variability between golf shots, we wouldn't expect the point estimate of 124.73 yards to exactly correspond to the target. So a point estimate by itself isn't very useful. We expect our point estimate to be close to the population parameter, but how close? That's a question answered by an interval estimate. An interval estimate is a range of values likely to include a target or population parameter. When an interval estimate includes a stated level of confidence, a probability such as 80%, then the interval estimate is called a confidence interval, and the probability is the confidence level. We observed that the golfer's shot landed at 124.73 yards, and we have prior knowledge that his shots are 80% likely to land within 5.28 yards of the target. The range of values within 5.28 yards of 124.73 yards is 124.73 minus 5.28 yards to 124.73 plus 5.28 yards. So we can say we're 80% confident that the range 119.45 to 130.01 yards includes the target. In this thought experiment, the unseen target represents mu, the parameter we're trying to estimate. The golfer's shot represents the sample from which we determine x bar, our point estimate for mu. And knowing that 80% of the shots will be within 5.28 yards of the target represents the knowledge we have about the sampling distribution. The formula for a confidence interval has this general form: point estimate plus or minus the margin of error. The point estimate is the sample statistic, and when we're constructing a confidence interval for the mean, the statistic is the sample mean, red X bar. The margin of error is the product of two factors, the critical value times the standard error of the statistic. When the statistic is the mean, this is the standard error of the mean. Let me give rough definitions of these two concepts. They'll both need refining later, so for now, please remember these are general, simplified definitions. The critical value is the z-score corresponding to a probability we determine using the stated confidence level. On our normal table, z-scores were color-coded blue as part of our memory aid, so I'll make the critical value blue because, for now, it's a z-score. When a z-score represents a critical value, it often has a superscripted asterisk, so it isn't easily mistaken for an ordinary z-score. The asterisk reminds us that it's a critical value used to determine a margin of error. And the standard error, for now, let's call it the standard deviation of the sampling distribution, pink sigma sub x bar. Don't let the word error in standard error alarm you. It doesn't mean we made a mistake. Standard error is a lot like standard deviation. It's just a natural random variation from the mean due to the nature of random variables. Statisticians use the word error to mean variability. It doesn't mean a mistake. I said in video 1 that we'd use the standard deviation as a yardstick, and here we can see the standard deviation of the sampling distribution, pink sigma sub x bar, is the yardstick, and the blue critical value is the number of yardsticks. So the confidence interval for the mean is red x bar plus or minus a blue number of pink standard errors. This is very important. It's the general form for all confidence intervals. Point estimate plus or minus critical value times standard error. So the confidence interval is a range of values centered on the point estimate x bar. The lowest value of the interval is x bar minus critical z times sigma sub x bar. The highest value is x bar plus critical z times sigma sub x bar. That's why we write a confidence interval as x bar plus or minus critical z times sigma sub x bar. Let me break this down and show you exactly what this is saying. Here's a sampling distribution. Remember from video 1 that the sampling distribution is the distribution of every possible sample mean. I've shaded the middle 80% that are within 5.28 yards of the mean, using our golf example. When we draw our sample, its mean x bar is a red point somewhere in this distribution. Put differently, our sample x bar is a random variable having this pink distribution. We don't know where it is in the distribution, but it has an 80% likelihood of being in the pink area, because that's where 80% of the sample means are. Since our sample will be in the pink area 80% of the time, that means that 80% of the time it will be within 5.28 yards of the true population mean, mu. So if we take our sample mean x bar and add and subtract the margin of error from it, 5.28 yards in this example, that will bracket an interval that's 80% likely to include the true population mean, mu. We don't know mu, but it's 80% likely to be in this interval, point estimate minus the margin of error, and point estimate plus the margin of error, and that's how confidence intervals work. There are confidence intervals for many statistics, confidence intervals for means, for proportions that we'll do later, for the difference between means, the difference between proportions, for the variance or standard deviation, for the slope of a regression line, and others. They all sound like very different things, but they're all confidence intervals with this format: point estimate plus or minus critical value times standard error. The red point estimate is always the statistic from your sample, so all you need to learn is how to find the blue critical value and how to find the pink standard error. Let's go back to our battery scenario from video 1, where we're interested in the mean lifetime of 9-volt batteries made at a particular factory. Let's construct the confidence interval. We already know the point estimate x bar is 382.9 minutes from video 1. That's our sample mean, the red sample statistic. And the pink standard error is sigma sub x bar, the standard deviation of the sampling distribution, which is the population standard deviation sigma divided by the square root of the sample size, n. All these numbers are from video 1. We get sigma sub x bar equals 6.1 minutes. The blue critical value depends on the desired confidence level. In this example, we'll use a confidence level of 95%. Now in video 1, we learned how to use a standard normal table to convert a yellow probability into a blue critical value by finding the probability in the body of the table and noting the associated blue critical value in the margins. But be careful, because 95% is not the yellow probability we need to find in the table. Here's how to find the probability we want, the one we'll use in the normal table. First, make a rough sketch of the PDF of a sampling distribution. It'll be bell-shaped, but it's okay to be sloppy. With practice, you can do this in your head, and you won't even need to make a sketch. Second, put the confidence level, 95%, in the middle of the PDF. Just make 2 lines out here, shade, and label the middle section with the confidence level to denote it's 95% of the total area, or whatever the confidence level is. The critical value we want is the z-score associated with this point. Because if we go up this many standard deviations from the mean, and down this many, we'll have covered 95% of the samples in the sampling distribution. Remember that the probability associated with the z-score is the cumulative probability up to that z-score, and in our example, it's not the confidence level, 0.95. It's 0.95 plus this tail. Since the area under the curve equals 1, the area in the tails must be 1 minus the confidence level. Here it's 1 minus 0.95, which is 0.05. In inferential statistics, this number has a special name. It's called alpha, or the alpha level. We'll talk about alpha more in video 3, where we'll call it the significance level. But since it's right here, I wanted to point it out. Alpha equals 1 minus confidence level. So alpha and confidence level are complements. Their sum always equals 1. Since the 2 tails add up to alpha and the normal curve is symmetrical, each tail represents an area, or probability, of alpha over 2. You'll see alpha over 2 a lot in your textbook, and this is why. So the yellow cumulative probability up to the blue critical z-score we want to find is confidence level plus alpha over 2. These 2 areas. Since the total area under the curve is 1, this is the same probability as 1 minus alpha over 2. For a 95% confidence level, the cumulative probability turns out to be 97.5%, or 0.975. Please don't think the z-score is 0.975. The area under the curve represents a probability, and we use the normal table to convert back and forth between yellow probabilities and blue z-scores. So now we find the blue z-score corresponding to 0.975. I know this is too small to read, but it's just like what we did in video 1. Find the probability in the middle, then read out to get the z-score. Here it's 1.96, the critical value for our confidence interval. We now have everything we need to construct our confidence interval for the mean battery life. Red x bar plus or minus blue critical value times pink standard error. 382.9 minutes plus or minus 1.96 times 6.1 minutes. So we have 382.9 minutes plus or minus 12.0 minutes. 12.0 minutes, remember, is the margin of error, which is critical value times the standard error. We state our confidence interval like this. We are 95% confident that the range 370.9 minutes to 394.9 minutes includes the mean battery life of the batteries produced in this factory. Always state the confidence interval as a full sentence in the context of the problem or scenario. Don't just say 382.9 plus or minus 12. In your sentence, include the confidence level, do the math to create an actual interval with units and context. Also, the confidence interval sentence should express our confidence in the interval, the range of numbers, not in the population mean. So even though it sounds right, we should not say we're 95% confident that the population mean lies within this interval. Rather, we'd say we're 95% confident that the interval contains the population mean. I argued with my professor that the two sentences said the same thing, but I hope you'll see sooner than I did that it's just more scholarly to make the interval the object of our confidence rather than the population mean. In fact, the most correct interpretation is to go up one level of abstraction and say that our confidence is in the procedure we used to generate the confidence interval. The confidence interval we construct by drawing a sample and doing the math either will or will not contain the population mean. But if we follow our sampling procedure over and over to produce 95% confidence intervals, then we'd expect the intervals to include the means 95% of the time. That's really what we mean when we express confidence in the interval we constructed. I'll demonstrate this shortly with another app from BFW, but first I want to look at constructing confidence intervals with different confidence levels. When we change the confidence level, only the blue critical value will change. Our sample mean, red X bar, doesn't change, and neither does the standard error, the standard deviation of the sampling distribution. The critical value depends on the confidence level, and only the critical value changes as the confidence level changes. The most common confidence level percentages are 90, 95, 98, and 99%. I'll add our memory aid diagram above. We put the confidence level percent in the middle of a bell-shaped PDF. Next, we determine the cumulative probability. This is the yellow value we'll look up in a normal table to find the blue critical value. It's the confidence level in the middle plus one tail, which is alpha over 2, or equivalently 1 minus alpha over 2. Up in the header, I'll put the memory aid. The cumulative probability is shaded yellow. When our confidence level is 95%, this turned out to be 97.5%. I didn't mention it before, but you can start at the confidence level and go halfway to 100% to get to the cumulative probability. So starting at 95%, halfway to 100 is 97.5%, the cumulative probability for the critical value. I want to emphasize that you shouldn't need to memorize these formulas if you understand what's going on. To convert a yellow cumulative probability into a critical value, we use the normal table. Here's the memory aid. The table tells us the z-value we want, the critical value for the confidence interval, 1.96 from video 1. Here's the confidence interval and the formula, red plus or minus blue number of pinks, which is x bar plus or minus critical value times standard error. When we plugged in the numbers a few minutes ago, we got this interval, 370.9 to 394.9 minutes. Now let's quickly do the other confidence levels. For a confidence level of 90%, we put 90% in the middle and then add one tail, 95%. We look up 95%, or 0.95, in the body of the normal table. We did this in video 1, but I'll do it again here for this one. Let's look for 0.95. It looks like we're exactly midway between 0.9495 and 0.9505. So read to the left to get 1.6, and read up to get midway between 0.04 and 0.05, so 0.045. This means the critical value z is 1.645. Plug in all three numbers and we get 372.9 to 392.9 minutes. We lowered the confidence level from 95% to 90%, and the confidence interval got narrower. This makes sense. With a narrower confidence interval, we're less confident that it includes the true population parameter mu. For a confidence level of 98%, we have 1% in each tail, so the probability corresponding to the critical value is 0.99. The z-value for 0.99 is 2.33, and our interval is 368.7 to 397.1 minutes. The range got wider since our confidence level was higher. For 99% confidence level, the cumulative probability is 99.5%. When we look up 0.995 in the normal table, we get a z-value of 2.575. This makes our interval 367.2 to 398.6 minutes. As we expect, The highest confidence level results in the widest confidence interval. You might think we could go a little further and provide a 100% confidence level, but let's see what happens when we try. With the confidence level of 100%, the cumulative probability is also 100%. Alpha is 0, so the confidence level plus alpha over 2 is 100%, or 1.0000. When we try to look up 1 in the z-table, we never find it. As z gets higher and higher, the cumulative probability gets closer and closer to 1, but never reaches it. So z is actually infinity. This makes our confidence interval negative infinity to positive infinity. Not very useful or insightful. So a 100% confidence interval would tell us nothing at all about the population. We knew the population statistic was between negative infinity and positive infinity before we drew our sample. The most common confidence intervals used are 90, 95, 98, and 99%, but never 100%. Let me show you a practical demonstration of the confidence interval concept. The BFW website has another good app linked in the description. On the right side, the black PDF represents the population which, for this demonstration, is normal, with mean mu denoted by the green vertical line. These sliders on the left side let us adjust the confidence level and sample size. The red dotted line PDF is the sampling distribution, whose standard deviation, sigma sub x bar, depends on the sample size n. Larger samples result in narrower sampling distributions. Here's the sampling distribution when the sample size is 10. And when the sample size is increased to 75, it becomes much narrower. We covered this in the last video when I demonstrated the central limit theorem. Since the central limit theorem tells us that the mean of a sampling distribution mu sub x bar equals the population mean mu, the green line also represents mu sub x bar. With the confidence level set to 95% and the sample size set back to 10, I'll click the green sample button and the app draws a sample of size 10 from the normal population. It plots the 10 random variable values here, some above the mean, some below. If it ever looks like fewer than n dots, then some are just very near each other. The app calculated the mean of the sample, that's the black dot. For the first example, I'm going to paint it red since that's our memory aid color for the sample mean x bar. The 10 dots represent our sample, and the red dot represents the red sample mean, x bar. And the line segments extending to the right and left of x bar denote the margin of error, plus and minus. Remember, the margin of error is, for now, blue critical z times pink sigma sub x bar. The app knows the critical value since we told it the confidence level 95%, and it knows sigma sub x bar since it knows sigma and n. Let me emphasize the interval boundaries with an orange and purple bar so the statement of our confidence level becomes, we are 95% confident that the range orange to purple includes the population parameter mu. And as we'd expect, with 95% confidence, the range does indeed contain mu. So if we drew samples over and over, and for each sample constructed a 95% confidence interval for the mean, we'd expect that the intervals would contain mu 95% of the time, and not contain mu 5% of the time. I'll click the Sample 25 button, and the app will construct 25 confidence intervals based on 25 new independent samples. Not all of them fit on the screen. And here we can see a confidence interval that does not include the population mean mu. The app highlights them by making them red. It doesn't mean there was a mistake, it just means that sometimes, by random chance, our sample mean x bar will be further away from the true mean than the margin of error. We control how often this happens when we choose the confidence level. The critical z-score we look up and use will result in intervals that include the mean x% of the time, where x% is the confidence level. Here, the app tells us how many confidence intervals we've generated, how many hit, which is how many include the population mean mu, and the hit percent. When the Sample 25 button is clicked repeatedly, the app keeps track of the totals for us. Here's the result after 1,000 samples. At a 95% confidence level, 947 out of 1,000 intervals include mu, a very good simulation. The app will let us change the confidence level without redrawing all the samples. So watch what happens when I reduce the confidence level to 80%. The confidence intervals all got narrower, and as a result, more intervals miss mu. Now, just 80% include mu instead of 95%. Actually, 796 out of 1,000. The intervals got narrower because the margin of error got smaller. Since the margin of error equals blue times pink, when we reduce blue, we reduce the margin of error, and we reduce the blue critical value by reducing the confidence level, like we did here from 95 to 80%. Now I'll drag the confidence level up to 99%. The confidence intervals got wider because the blue critical value increased, and since the intervals are wider, they're more likely to include mu. For our 1,000 samples, 990 intervals include mu. Now, before I continue, let me recap what I'm demonstrating with this app. First, the confidence level we choose corresponds exactly to how likely a confidence interval is to include the target mu. In this latest example, the confidence level of 99% means that, in the long run, 99% of confidence intervals will include mu. Second, the width of the confidence interval, the margin of error, depends on two factors: the stated confidence level, since higher or lower confidence levels result in higher or lower values for the blue critical value. And the width depends on the sample size. Higher sample sizes will result in lower values of pink sigma sub x bar, the standard deviation of the sampling distribution. So, with the confidence level still set at 99%, I'll increase the sample size to 150. But first, note the width of the red sampling distribution. This is a review from video 1. And as we just said, as the sample size increases, the sampling distribution gets narrower, since the standard deviation of the sampling distribution, sigma sub x bar, equals the population standard deviation sigma divided by the square root of the sample size. So here's the sampling distribution for n equals 150, much narrower. The app wiped out our 25 samples since the sample size changed, so we draw 25 new samples of size 150. And notice that the confidence intervals got narrower. But in the long run, we still expect 99% to include mu. The link to this app is in the description. I think you can build your understanding by experimenting with and changing the settings on your own. Okay, let's do a fresh problem. This time batteries from a competitor. We randomly buy 50 of our competitors' batteries and test their lives. The sample mean is 368.8 minutes, and due to espionage within the battery industry, we know that the standard deviation of their mean lives is 55.2 minutes. Construct a 95% confidence interval for the mean battery life mu. Pause if you like to do this one on your own. It's easy. X bar plus or minus critical z times sigma sub x bar. All confidence intervals are based on a formula that look like this one. We're given x bar here. Critical z always depends on the confidence level, and we can determine sigma sub x bar from the population standard deviation sigma and sample size n. X bar is 368.8 minutes. Sigma sub x bar is sigma divided by the square root of the sample size. 55.2 minutes divided by the square root of 50 equals 7.81 minutes. And you might remember that the critical z value for a 95% confidence level is 1.96. But if not, 95% is in the middle, plus 2.5% in a tail equals 97.5%. Look up 0.975 in a normal table, and we get 1.96. I'm skipping the arithmetic to focus on inferential statistics concepts, but we get 353.5 to 384.1 minutes. So, we are 95% confident that the range 353.5 minutes to 384.1 minutes includes the mean battery life of our competitors' batteries. Now, let's solve the same problem for a 98% confidence interval. Only one of our three component numbers will change. Which one? It's the critical z value. It depends on the confidence level. The sample mean x bar hasn't changed, and the standard deviation of the sampling distribution hasn't changed. With a confidence level of 98%, we look up 0.99 in the normal table. With practice, you won't need to draw a sketch. Look up 0.99 in the normal table, and we get a critical z-value of 2.33. We are 98% confident that the range 350.6 to 387.0 minutes includes the mean battery life of our competitors' batteries. Okay, another quick variation. Staying with a confidence level of 98%, let's assume the sample size was 100 rather than 50. Would you expect the confidence interval to get narrower or wider? As the sample size gets larger, the standard deviation of the sampling distribution gets narrower. We demonstrated this with the app. Since pink sigma sub x bar gets smaller, the margin of error gets smaller, so the confidence interval will get narrower. X bar is still 368.8 minutes. Critical z is still 2.33, since the confidence level is still 98%. Sigma sub x bar becomes 55.2 minutes divided by the square root of 100, which is 5.52 minutes. So with a sample size of 100, we are 98% confident that the range 355.9 to 381.7 minutes includes the mean battery life of our competitors' batteries. Here's a problem to check our understanding. Suppose a statistician takes a random sample of 20 planks from a lumberyard, measures their length, and states that she's 95% confident that the average plank length at the lumberyard is between 1.74 meters and 2.10 meters. What's the population standard deviation, sigma, the statistician used in her analysis? This is a contrived problem to shine some light on our understanding of the confidence interval formula. We'd probably never back into sigma like this. Well, all we know is the sample size n equals 20, the confidence level 95%, and the confidence interval. Here's the confidence interval formula. We know that sigma sub x bar, the standard deviation of the sampling distribution, equals the population standard deviation sigma divided by the square root of the sample size n. Since we know n, once we find sigma sub x bar, we can find sigma as asked. So that's where we're heading. We don't know any of these values directly, but since the confidence interval is centered on x bar, we know x bar must be right between 1.74 and 2.10 meters, their average, which is 1.92 meters. The margin of error is the distance from x bar to either interval endpoint. We'll just focus on the right half. The margin of error is critical z times sigma sub x bar. On the diagram, it's the distance from x bar to the endpoints of the confidence interval. 2.10 meters minus 1.92 meters equals 0.18 meters, which is equal to critical z times sigma sub x bar. As we've seen several times, the confidence level 95% is associated with a critical value of 1.96. So 1.96 times sigma sub x bar equals the margin of error, 0.18 meters. Dividing both sides by 1.96, and we have sigma sub x bar equals 0.0918 meters. Since sigma sub x bar equals sigma divided by the square root of 20, sigma must be equal to sigma sub x bar times square root of 20. So sigma equals 0.410 meters, which is what we were asked to find. So let's check our work by seeing if we can duplicate hers. Her sample size of 20 planks had a mean length of 1.92 meters. She used a value of 0.410 meters as the population standard deviation, sigma. Her confidence level was 95%. She created a 95% confidence interval as 1.92 meters plus or minus 1.96 times 0.410 over the square root of 20. This results in the same confidence interval she constructed. Confidence interval problems can be fast and painless with practice. Okay, we're not quite done because I said earlier that some definitions I provided would need to be refined. I said for now, let's consider the pink standard error to be the standard deviation of the sampling distribution sigma sub x bar. Well, sigma sub x bar is the population standard deviation sigma divided by the square root of the sample size. We showed this with the demo in video 1. The problem is we almost never truly know what sigma is. For our battery example, I told you sigma was 43.2 minutes, but that was just so we could plow through the explanation and get to the confidence interval equation. Same thing with the competitors' batteries and with the Plancks. The fact is, well, since the standard deviation's calculation is based on subtracting the population mean, mu, from every random variable in the population, we need to know mu in order to determine the standard deviation sigma. So it seems kind of silly to assume we don't know mu, but we do know sigma, because knowing sigma depends on knowing mu. So we've hit a snag. In order to construct a confidence interval, we need to know the standard deviation of the sampling distribution sigma sub x bar, which we could get if we knew sigma. Sigma tells us how spread out the population's random variables are. Are they bunched up close together? Are they spread out wide? We don't know sigma, so how can we tell? Well, we took a sample, and the variation in the sample somehow reflects the variation in the population. In fact, in video 1, when calculating S, the sample standard deviation, we divided by n-1 instead of n to make S a better estimator of sigma. Even so, it's not perfect, but it's the best we can do. So, we use the standard deviation of the sample, lowercase s, divided by the square root of the sample size as a substitute for the standard deviation of the sampling distribution, sigma sub x bar. This has an important implication we'll get to shortly, but first, some vocabulary. When we estimate the standard deviation of the sampling distribution using the standard deviation of the sample, the estimate is called the standard error of the statistic. And since the statistic we're talking about is the mean, this estimate is the standard error of the mean. It's our best estimate of the standard deviation of the sampling distribution, sigma sub x bar, based on the standard deviation of the sample, s, instead of sigma. The symbol for standard error of the mean is lowercase s sub x bar. You might also see capital SE sub x bar. SE stands for standard error, or SEM, standard error of the mean. I'll use lowercase s sub x bar, which can be transliterated as the standard deviation of all possible sample means. The formula is s divided by the square root of n. As you can see, we simply use s instead of sigma, and it's pink because it plays the same role as sigma sub x bar in the confidence interval formula. In the unusual case where we know sigma, we can calculate and use sigma sub x bar, the standard deviation of the sampling distribution. In the more common case where we don't know sigma, we calculate and use s sub x bar, the standard error of the mean. Sometimes these two concepts are collectively called the standard error of the mean. That's why in the general confidence interval formula, the term is called standard error, even though it might mean sigma sub x bar if you know sigma. For our memory aid, they both refer to the pink factor. Now, using s instead of sigma to calculate the standard error has an important implication. There is some added uncertainty because the standard deviation of a sample can be different than the standard deviation of the population from which it was drawn, even when we divide by n-1 instead of n. Due to the added uncertainty, we cannot use the normal table to find critical values. We use another bell-shaped curve I'll tell you about shortly. To use a z-value from a normal table as the critical value, two things must both be true. First, the sampling distribution must be approximately normal. This constraint isn't so bad. As we showed in the video 1 demo, when the sample size is greater than or equal to 30, the sampling distribution is pretty close to normal. Or when the population itself is normally distributed, then the sampling distribution will be normal regardless of the sample size. So number 1 is often true. But second, we must know the population standard deviation sigma. This is the one that almost always trips us up. I know I've said this 100 times, but in real life we hardly ever know sigma. But often, in test or homework problems, you'll be told sigma to test your ability to do the math using critical z-values. So when either of these two conditions is not met, we use a different PDF to find the critical value, not the normal PDF like we have been doing. The curve is called a t-curve or t-distribution with a lowercase t. It's flatter than a normal curve with less probability density in the middle, but since it's a PDF, it must bound an area of 1. So more probability density is pushed out into the tails. Let me show you very simply why we use the t-distribution. Here's a normal curve. To find the critical value corresponding to a particular confidence level, we put the confidence level in the middle, add the left tail to get the yellow probability we look up in the normal table to get our critical z-value. With the t-distribution, we do the same thing, but there's more probability out in the tails. So when we go through the same procedure, the critical t-value we get is always larger than the critical z-value for the same confidence level. This is to account for the extra uncertainty in using the standard error of the mean as an estimator for the standard deviation of the sampling distribution. Since the blue critical value is higher, the resulting confidence interval will be wider. When we know sigma, and so we know sigma sub x bar, and we know the sampling distribution is normal, we can use a critical z-value from a normal table and sigma sub x bar to construct our confidence interval. Otherwise, we must use a critical t-value and the standard error of the mean to construct the confidence interval, which will be wider. You may hear the t-distribution called student's t, and no, it's not named after you. The statistician that developed it wrote his papers using the pseudonym student. One story says his employers didn't want him publishing papers for the competition to read, so he hid his identity. He used the letter t in his papers to represent variables from this distribution, so when others referred to it, rather than just calling it t, which might be unclear, they called it student's t, and the name has stuck. When we have a large sample, then the standard error of the mean, S sub x bar, is a pretty good estimator of sigma sub x bar. When the sample is smaller, not as good. With larger samples, there's less uncertainty. This means we don't need as big an adjustment with the critical t-value we use. The larger the sample size, the closer critical t can be to critical z, because there's not as much uncertainty for t to account for. So how do we do that? Well, the fact is, the t-distribution is a family of bell-shaped curves. Each curve is denoted by its df, or degrees of freedom. For our purposes, df is equal to the sample size n minus 1. Here's the curve for degrees of freedom equals 1. Here's degrees of freedom equals 2. Here's degrees of freedom equals 5. The higher the degrees of freedom, meaning the greater the sample size, the closer the t-curve gets to a normal z-curve. I want to show you a t-table of values by comparing it to the normal z-table we've been using, which was covered in video 1. For inferential statistics, we have a confidence level plus alpha over 2, which represents the yellow cumulative probability that we look up in the body of the normal table to find the corresponding blue critical value. But the two tables are organized very differently. In the z-table, the probabilities are in the body of the table, and we read out to the margins to find the critical value. Since the t-distribution is a family of curves, there's data for many curves on one chart. Each row in a t-table represents a different degree of freedom, and only the most common probabilities used for inferential statistics are included, and they're listed across the top. Then the corresponding critical t-value is in the body of the chart. Each critical value depends on the degrees of freedom and the cumulative probability. So the normal z-table has probabilities in the body and critical z-values in the margins. And the t-table has critical values in the body and probabilities in the top margin. Let's build our confidence with a problem. From a population whose standard deviation we don't know, we draw a sample of 13 widgets and measure a continuous random variable such as their mass. What's the critical value we should use to generate a 95% confidence interval for the mean? Okay, first, we're not being asked to construct a confidence interval. Not yet. We're just being asked what blue critical value we'd use. We don't know the population standard deviation sigma, so we can't know the standard deviation of the sampling distribution sigma sub x bar, because sigma sub x bar equals sigma divided by the square root of the sample size. Since we don't know sigma sub x bar, we must estimate it with the standard error of the mean, S sub x bar. And when we use S sub x bar to estimate sigma sub x bar, we'll use t instead of z to account for the extra uncertainty in using s sub x bar as a substitute for sigma sub x bar. Now, this was a detailed explanation of the reasoning to aid your understanding. Eventually, the thought process simply becomes, do you know sigma? Then use z and sigma sub x bar. If you don't know sigma, use t and s sub x bar. So, let's solve this problem. Z and t follow the same steps. Draw a bell shape, put the confidence level in the middle, add the left alpha over 2 tail, and we get 97.5%, or 0.975. We'll use the t-table and find this probability in the top margin. We'll find our critical t-value in this column. To figure out which row to use, we need the degrees of freedom, which is sample size n minus 1. 13 minus 1 is 12, so reading across the 12 row, we get a critical t-value of 2.179. Note that if we knew the population standard deviation, we would use the z-table to determine the critical value, and would have found 1.96. As I said earlier, critical t-scores are higher than corresponding z-scores at the same confidence level. As you can see from this column, critical t-values increase as the sample size decreases. Again, if we knew sigma sub x bar, then the critical z-value would always be 1.96 for this confidence level, regardless of the sample size. But when we estimate sigma sub x bar with s sub x bar, the higher values for critical t account for the uncertainty, and there's more uncertainty to account for with smaller sample sizes. So as sample sizes increase, critical t will get gradually smaller, closer and closer to the critical z-value for the same confidence level. Let's do another lumberyard plank length problem. We measure 17 randomly selected planks at a lumberyard and find their average length is 1.78 meters. The variance of the 17 plank lengths is 0.0577 meters squared. Construct a 90% confidence interval for the average length of all the planks at the lumberyard. Let's write out our confidence interval formula and see where we stand. Well, x bar equals 1.78 meters, so we have one of our three values. The method by which we find the other two depends on if we can determine sigma sub x bar. We're told the sample variance, but nothing about the variability of the population. So we'll need to use the standard error of the mean, s sub x bar, as an estimator for sigma sub x bar, and as a result, use t critical values instead of z. Let's find the critical t value. The confidence level we were told to use is 90%. So the cumulative probability adds one tail of 5%, so the probability we'll look up is 95%, t sub 0.95. The degrees of freedom is the sample size minus 1, so 16. We get 1.746. Now for s sub x bar. It's the standard error of the mean, which is s, the standard deviation of the sample, divided by the square root of the sample size. We're told the variance of the sample, not the standard deviation. Don't make the mistake of using variance as standard deviation. Standard deviation equals the square root of variance, so square root of 0.0577 meters squared is 0.240 meters, not squared. Dividing that by the square root of the sample size gives us the standard error of the mean, 0.0582 meters. We now have everything we need to construct the confidence interval. Skipping the arithmetic, we are 90% confident that the range 1.678 to 1.882 meters includes the average length of planks at the lumberyard. We've covered confidence intervals for continuous random variables. Now we'll go over the confidence intervals for proportions, another common population parameter. By proportion, we mean the proportion or fraction of a population having a particular characteristic. Here are some examples. The proportion of voters who intend to vote for our candidate. The proportion of 2-liter bottles underfilled at a bottling factory. The proportion of fast food orders that include a beverage. The proportion of basketball shots made during a game. In each case, the characteristic is a binary variable that has only two possible states, which we call success or failure, depending on what we're interested in counting. And the proportion is the number of successes in the population divided by the size of the population. So proportions are determined by counting, not by measuring. For our examples, a population member having these characteristics is counted a success. A population member that doesn't is a failure. Note that even characteristics that are negative, such as an underfilled 2-liter bottle, are still called successes. With proportions, the words success and failure don't mean good and bad. They mean what we're counting or not. Let me start with a chart and we'll begin defining terms. The population proportion is denoted by lowercase p and is the number of successes in the population, capital X, divided by the population size, capital N. You can think of p as the population average if successes were to count as 1 and failures as 0, the proportion of successes in the population. So p is also the probability that any randomly chosen member of the population will be a success. Now for the variance of a population proportion. The symbol is sigma squared, the same as for continuous random variables, but the expression turns out to be the very simple p times q, where p is the proportion of successes and q the proportion of failures. Since every random variable is either a success or failure, q equals 1 minus p. Let me show you how we get pq for the variance. Remember from video 1 that the variance is the average squared distance between each random variable value and the population. It's the same for variance of the proportion, except there are only 2 random variable values, success and failure, to which we'll assign the values 1 and 0, and we subtract the population proportion, p, in place of mu. For simplicity, let's say our population has 10 members, 5 successes and 5 failures. The proportion p equals x over n, the number of successes divided by the population size. 5 successes out of 10 equals 0.5, which is the population proportion. If there were 9 successes and 1 failure, p would be 9 out of 10, or 0.9 here. And for 1 success and 9 failures, p would be 1 over 10, which is 0.1. Now that we can find the proportion p, let's find the variance. Back to the scenario with 5 successes and 5 failures, p equals 0.5. The variance is the average squared distance between each point and p. Let's find the sum of all 10 squared distances, then divide by the population size n to find the average. This will be the population variance. We'll do the 5 successes, then the 5 failures. Each success has the value 1, and p equals 0.5. So this distance is 1 minus 0.5, which is 0.5. We want the squared distances, so 0.5 squared is 0.25. And there are 5 successes, so 5 times 0.25 equals 1.25. For each failure, to which we attribute the value 0, the distance is 0 minus p, which is 0 minus 0.5, or negative 0.5. Negative 0.5 squared is positive 0.25. And again, there are 5 failures, so 5 times 0.25 is 1.25. Add them together, and the sum of these squared distances is 2.5. To find the average squared distance, we divide by the population size n to get 0.25. Now let's say p equals 0.6. We have 6 successes, each is 0.4 away from p. 6 times 0.4 squared is 0.96, the total squared distance for the 6 successes. We also have 4 failures, 0.6 away from p. 4 times 0.6 squared is 1.44, the total squared distance for the 4 failures. So the proportion variance, sigma squared, is 0.24. One more, let's say p equals 0.2. For successes, 2 times 0.8 squared is 1.28. For failures, 8 times 0.2 squared is 0.32. So the proportion variance, sigma squared, is 0.16. Now let's review these results. When p was 0.5, the variance, sigma squared, was 0.25. When p was 0.6, the variance was 0.24. And when p was 0.2, the variance was 0.16. As it turns out, for proportions, sigma squared will always equal p times q. The math is the same as for continuous random variables, it just turns out to be equal to a very simple expression for the variance of proportions. And so the standard deviation of the population proportion sigma is the square root of p times q. Now for the sample statistics. The proportion of the sample is denoted by p hat, a lowercase p with a hat on top. I don't know why x bar has a bar and p hat has a hat. Maybe some mathematician could tell us in the comments. I'm just an engineer and I don't know. P hat equals lowercase x divided by the sample size n. Lowercase x is the number of successes in the sample. Uppercase X, remember, is the number of successes in the population. The sample variance is labeled s squared, just like for continuous random variables. It's p hat times q hat, where q hat is the proportion of failures in the sample. P hat plus q hat equals 1, so q hat equals 1 minus p hat. The sample standard deviation, lowercase s, is the square root of p hat times q hat. Here's a very important point about the standard deviation of the proportion of the sample. It's an unbiased estimator of the population standard deviation, sigma. This is different than the standard deviation of the mean of a sample, which is biased. P hat times q hat is an unbiased estimator of p times q. This will come up in a moment. In order to construct confidence intervals for proportions, we need to know the characteristics of the sampling distribution of p hat to determine the pink standard error. The sampling distribution of the proportion is comprised of all the possible sample proportions of a particular size. The mean of the sampling distribution has the symbol mu sub p, which can be transliterated as the mean of all the proportions. It's equal to the population proportion p. This is just like the mean of the sampling distribution of means, mu sub x bar, was equal to the population mean mu, from video 1. Of course, we never truly know p, which is why we're constructing a confidence interval for it. The standard deviation of the sampling distribution has this symbol, sigma sub p. Just like for means, it's the population standard deviation sigma divided by the square root of the sample size. Sigma is the square root of p times q, so pink sigma sub p equals the square root of pq over n. And just like for continuous random variables, we don't know sigma. So again, we'll use the sample standard deviation, s, as an estimator for sigma. So the standard error of the mean becomes square root of p hat times q hat divided by n. Remember, I said that s was an unbiased estimator of sigma. This means that when we use square root of p hat times q hat divided by n as an estimator of sigma sub p, we don't have to account for any extra uncertainty, so we can use z instead of t to find the critical value. There is a double condition to check for, but they're often true. I'll go over the condition after we do our first problem, but the practical point is that when constructing confidence intervals for proportions, we use z-tables. Let's do a problem. A new student at a large high school notices a lot of left-handed classmates. She randomly selects 100 classmates and asks if they are right or left-handed. 13 are left-handed. Construct a 90% confidence interval for the true proportion of left-handed students at the high school. Here's the confidence interval formula. P hat, the sample mean, is our point estimate. 13 divided by 100, since a left-handed student, is counted as a success, so 0.13. For the critical value, we can use a z-score from a normal table. The probability we look up is the given confidence level plus alpha over 2, which is 90% in the middle plus one tail of 5%. So the z-score corresponds to 95%, which is 1.645. And the standard error is the square root of p hat times q hat over n. P hat is 0.13, so q hat must be 0.87. The sample size n equals 100. The square root of 0.13 times 0.87 divided by 100 is 0.0336. And we have everything we need to construct the confidence interval. We're 90% confident that the interval 0.0747 to 0.1853 includes the true proportion of left-handed students at the high school. Easy. We'll do another problem after two important notes. First, a little more on why we don't have to use t for proportions. When discussing confidence intervals for means, I said the critical value is a z-score only if both of these were true. We must know that the sampling distribution is normal, and we must know its standard deviation. The central limit theorem assures us that the sampling distribution will be very close to normal if the sample size is large enough, over 30. But we also need to know its standard deviation, sigma sub x bar. To know sigma sub x bar, we need to know sigma, since sigma sub x bar is sigma divided by the square root of n. And we just don't know sigma. We have to use the biased estimator S, the sample standard deviation, as a substitute, which is better than nothing, but not good enough to use the narrower normal distribution. So we must use the t-distribution to find critical scores for means. For proportions, the same two criteria apply, but the story's a little different. Let me start with the second condition. We must know sigma sub p, the standard deviation of the sampling distribution. Again, it depends on knowing sigma, the standard deviation of the population, which we never truly know. But the sample standard deviation, S, is an unbiased estimator of sigma. In fact, it's a great estimator, and when we use it to calculate the standard error, like we did in the left-handedness example, there's no additional uncertainty introduced, and the criteria is met. We have a great estimator of sigma sub p. For the first criteria, we need to note that the sampling distribution is normal. This is often the case with proportions, and we can check it with the double condition I mentioned earlier. I'll do a demonstration of these conditions next. But assuming they're met, the sampling distribution will be very nearly normal, and we can determine critical values from the normal z-table. And that's why we don't have to use t-distributions for proportions. Here's another app from the BFW webpage, linked in the description. The yellow bars show the binomial distribution, which is closely related to the concept of proportions. Let me show you how. With these sliders, we set the sample size and population proportion, which is the same as the probability of randomly choosing a success from the population. We'll simulate tossing a coin 40 times and consider heads a success. So we set p equal to 0.5, assuming we have a fair coin, and n to 40 to simulate 40 coin tosses. The yellow bars show the likelihood of different numbers of successes in the experiment. As you might expect, 20 is right in the middle. From 40 tosses, we'd expect a number near 20 heads in this region. We'd almost never expect to see fewer than 10 or more than 30. That's what the binomial distribution shows us, the likelihood of different numbers of successes for particular values of n and p. If we were to divide the numbers on the horizontal axis by n, which here is 40, then the distribution would be the sampling distribution of the proportion, because p hat equals number of successes divided by n. So we can recap the numbers from our earlier chart. Here are all the different values for the sample proportion p hat from 0 to 1. The mean of all the possible samples is mu sub p hat, which equals the population proportion p, 0.5. Sigma sub p hat is the standard error, the standard deviation of the sampling distribution, which is the square root of pq over n. For p equals 0.5 and n equals 40, this turns out to be 0.079, which is about this length based on the scale of the horizontal axis. Now I want to show you the double condition to check if we can use the normal distribution to find the critical value. The conditions are easy to remember: np hat greater than or equal to 10, and nq hat greater than or equal to 10. Since p hat equals number of successes divided by n, when we multiply both sides by n, we get np hat equals number of successes, and likewise nq hat equals number of failures. So the double condition is simply that the sample has at least 10 successes and at least 10 failures. Here's where that rule comes from. As you can see, the red normal curve matches the data extraordinarily well, and on the average, we have 20 successes and 20 failures, both greater than or equal to 10. As we reduce p, the mound shape moves to the left. At p equals 0.25, there are 10 successes and 30 failures, both greater than or equal to 10, and the red normal curve still closely approximate the sampling distribution. When the mound gets near the left edge, say p equals 0.05, The yellow bars become right-skewed, and the red normal curve no longer fits so well, and even gets cut off on the left edge. The normal curve no longer fits the sampling distribution. Stating that NP hat, the number of successes, is greater than or equal to 10 pushes us out here, ensuring that the sampling distribution is very nearly normal. And NQ hat greater than or equal to 10, at least 10 failures, does the same thing on the right side. When both conditions are met, we're in the safe zone and can use Z for our critical value. 2 notes. First, it's not easy to construct a confidence interval when these conditions are not met. If you use the normal approximation, you'll get bad results. In high school and first-year college inferential statistics, the conditions will almost always be met, but you will be expected to do the checks and state explicitly that NP hat is greater than or equal to 10, and NQ hat is greater than or equal to 10, so you can use the normal approximation of the binomial distribution to find the critical value. Second point, some instructors and textbooks use a cutoff value of 5 instead of 10, and I've even seen 15. My advice is to agree with your instructor, but it may be enlightening to try out this applet yourself and see what you think for different values of N and P. Let's do another problem. A political candidate's research team polls 300 randomly selected voters for a statewide election. 161 voters support the candidate, and 139 do not. Construct a 95% confidence interval for the true proportion of voters who support the candidate. First, let's check the assumption that we can use the normal curve. NP hat and NQ hat are both greater than or equal to 10. That is, 161 and 139 are both greater than or equal to 10. So we can use the normal curve and table to find the critical value. Okay, we just need to find 3 numbers. P hat equals the number of successes divided by the sample size. So P hat equals 161 divided by 300, which is 0.53667. We'll need Q hat too. It's 1 minus P hat, or 0.46333. The critical Z value for a 95% confidence level is the Z-score associated with a probability of 0.975, which is 1.96. And the standard error is the square root of P hat times Q hat divided by N. Plugging in the appropriate numbers yields a standard error of 0.02879. Well, all the hard work is done. We just need to compute the range and state the confidence interval. We are 95% confident that the interval 48.02% to 59.31% includes the true proportion of voters who support the candidate. Since the range includes proportions below 50%, the candidate cannot be confident that he has a lead, even though P hat was 53.557%. The candidate isn't satisfied and says he wants an estimate with a plus or minus 3% margin of error, like he hears on the news. What would you tell the candidate? To reduce the confidence interval, we can either reduce the confidence level, which will result in a lower critical value and hence a smaller margin of error, or we can increase the sample size. The candidate doesn't want to reduce the confidence level, so what sample size is needed for a margin of error plus or minus 0.03? We want the margin of error to be less than or equal to 3%, or 0.03. So critical value times the square root of P hat times Q hat over N must be less than or equal to 0.03. We can't change the critical value, it's 1.96 based on the confidence level. What about P hat and Q hat? Can we use P hat and Q hat from our first sample? Well, that's a possibility. When you don't have any idea what the true proportion is, it's customary to set P hat and Q hat both to 0.5. This is the conservative approach that maximizes the standard error, so we don't provide a confidence interval narrower than what's appropriate. So our equation becomes 1.96 times square root of 0.5 times 0.5 divided by the square root of n is less than or equal to 0.03. I'm distributing the radical to the numerator and denominator. Let's isolate n by multiplying both sides by square root of n, and then divide both sides by 0.03. To get n instead of square root of n, let's square both sides and simplify. N is greater than or equal to 1067.11. Since n must be a whole number, we'll need to use 1068. This is actually a real-life application. Pollsters will often have sample sizes near 1100 to provide relatively small margins of error. So, for the sake of completeness and to get a little more practice, let's repeat the problem with a sample size of 1068. When we conduct this poll, we find 550 support the candidate and 518 do not. So, p hat equals 0.51498. Q hat equals 0.48502. There's no change to the critical z-value since it depends on the confidence level, which is still 95%. And after a little math and square roots, the standard error is 0.01529. Here's our confidence interval formula. The right term is the margin of error, and let's note that it is less than or equal to 0.03. It shouldn't be a surprise since we calculated what n should be so that we would have this exact result. And our statement becomes, we are 95% confident that the interval 48.50 to 54.49% includes the true proportion of voters who support the candidate. In political coverage, you'll often hear p hat plus or minus the margin of error, so something like 51.5% with a 3% margin of error. All confidence intervals have this format: point estimate plus or minus critical value times standard error. Here's a summary chart of the proper values for means and proportions. When encountering a confidence interval technique for a new type of statistic, just focus on how to determine these values. You'll find confidence intervals are quite easy. In the next video, we'll cover hypothesis tests, where we'll learn how to test claims about a population based on a sample.